Hi, I'm Dominik, and this is Modular Collaborative Program Analysis in OPAL, which is joint work with my colleagues Florian Kübler, Reif, Eichberg, and Mira Mezini from the Software Technology Group of the Technical University of Darmstadt. When we implement static analyses, we try to improve their soundness and precision. This leads to analyses becoming ever more complex. Thus, in order to cope with this complexity, we need to build complex analyses from individual, decoupled, modular sub-analyses in a plug-and-play fashion. At the same time, of course, we need to keep an eye on performance, as the programs we try to analyze get larger as well. The two traditional paradigms of implementing static analyses, however, fail these goals. Imperative implementation allows for a flexible choice of algorithms and data structures, making it possible to implement any analysis with a reasonable performance. But approaches to modularize and parallelize such analyses have been ad hoc, constructed for specific kinds of analyses, and need to be re-implemented or even rethought in order to apply them to different analyses. Declarative analyses, often based on data log, on the other hand, provide modularization and parallelization out of the box. However, the choice of algorithms and data structures is fixed by the underlying solver, thus limiting what analyses can be implemented and how they can be optimized. Thus, in OPAL, we implemented a novel, hybrid approach that is reminiscent of a Blackboard architecture. A central storage, the Blackboard, keeps track of all analysis results, and its fixed-point solver coordinates the execution. Thus, the central infrastructure decouples the individual analyses and provides modularization and parallelization. The analyses themselves, on the other hand, can be implemented freely in an imperative manner, giving them full control of the algorithms and data structures used internally. This approach allows for complex systems of analyses with many interdependencies, such as in the example shown here. Analyses for purity, different kinds of mutability and escape information mutually depend on each other, as well as on a 3-address code intermediate representation and a call graph. Many of these dependencies are optional, based on what specific analysis module is used for each of the analyzed properties, enabling trade-offs in soundness, precision, and performance in a plug-and-play fashion. So, let's delve deeper into the features that enable this flexibility. First, the analysis results are taken from lattices that are reified in OPAL. This enables analyses to depend only on these lattices, not on specific other analyses. Also, the reified lattices can provide information to the solver for checking correctness or more efficient scheduling. The lattices can also contain fallback values to be provided in place of an actual analysis result, and default values that are used when individual entities aren't analyzed, for example, because a method is unreachable. These values don't have to be fixed in advance, but they can be provided by simple functions without dependencies for more flexibility and precision. This snippet of Scala code is an example of a very simple lattice for class mutability as it is implemented in OPAL. As you can see, it does not require more than a few simple classes and methods. Of course, developers can add more information, such as the actual lattice ordering, to guide the solver, but this is not required. Analyses in OPAL are structured in two parts. First, an initial analysis function is used to traverse code, providing an initial result and collecting dependencies on other analysis results. A continuation function is later invoked by the fixed-point solver whenever an update to a dependency is available. Thus, analyses are executed as shown here. The initial analysis functions work imperatively, querying the Blackboard for the current state of dependencies. When they produce an initial result and a list of open dependencies, the fixed-point solver takes charge like in declarative systems. It repeatedly invokes the continuation functions when dependencies are updated, and the continuation functions report updated results to the Blackboard. This process is performed until quiescence is reached, that is, until no further updates are generated. This structure has three main benefits. First, it allows for a flexible, imperative implementation that can handle stateful computations even in the presence of parallelization. Second, as the initial analysis function is invoked only once, the analyzed code does not have to be traversed multiple times. Third, because results for dependencies are not required immediately but are provided via the continuation function later on, computation is asynchronous and dependencies can be cyclic. We combine this imperative implementation with more declarative specifications. Every analysis specifies the lattices of its results and dependencies, the way it refines its intermediate results, that is, whether the analysis is optimistic or pessimistic in nature, and which entities the analysis is going to analyze. For the latter, there are several options available to analyses in OPAL. One can analyze a pre-selected set of entities, such as all methods of the analyzed program. But analyses can also be started on demand, only for entities for which a result is required, either by the end user or by another analysis. Another option is to start an analysis once some other property has been computed. We use this feature extensively in our call graphs, where a method is only analyzed once it is found to be reachable. Finally, OPAL allows analysis developers to preset some values, for example for known base cases or entities that have been analyzed previously, possibly manually or by external tools. Analyses are also flexible in how they return their results, either one result at a time or multiple results at once. These results can either be a single value taken from the result lattice or a function that applies some delta to the current state of the analyzed property. This allows for several analyses to collaborate in the computation of a single result. Using these features, we implemented several case studies to show how dissimilar analyses can be implemented in OPAL. Besides the mutability, escape, and purity analyses shown earlier, this includes the computation of an intermediate representation that is based on abstract interpretation and that includes optional modules to refine the types of fields and method return values. Our call graph case study consists of different base algorithms such as class hierarchy analysis, rapid type analysis, and a context-insensitive points-to analysis that can be extended with individual modules for language features such as reflection, serialization, threads, and more. Finally, we implemented a solver for interprocedural, finite, distributive subset problems as an individual analysis on top of our general solver infrastructure, showcasing the flexibility of the framework. Thus, we conclude that OPAL's programming model allows for many dissimilar analyses to be implemented as sets of comprehensible, maintainable, and pluggable sub-analyses. We can use this flexibility to explore trade-offs between soundness, precision, and performance. These two tables show the results of different configurations for a purity analysis as well as a call graph analysis. The left one shows different precision purity analyses combined in a plug-and-play fashion with different precision escape and or field mutability analyses. While more precise analyses clearly find a larger number of pure methods, this comes at the expense of significantly more computation time. However, almost all of the additional precision can be achieved with a configuration that is, in theory, less precise, but is more than 2 times faster. Similarly, the table on the right shows the rapid type analysis call graph combined with different optional modules for different language features. We can see how different modules affect the soundness of the result as given by the number of reachable methods, and the runtime cost for achieving this additional soundness. Being plug and play, just configuring different analysis combinations for execution, OPAL facilitates systematic investigation of such different configurations. This supports end users and analysis developers in finding the best trade-offs between precision, soundness, and scalability. But how does it perform? We compared our context-insensitive points-to analysis to DUPE, the state-of-the-art in declarative points-to analysis. Our implementation is 9% faster than DUPE's analysis phase, and DUPE additionally requires compilation and fact generation phases that have significantly more computation time. And this result is with our implementation having to analyze almost twice as many methods for the Eclipse project, as our reflection handling uses a more sound approach. So, despite being more general, OPAL supports implementing points-to analyses that clearly outperform DUPE. Finally, we obtained some promising initial results on parallelization. While our parallel solver is not yet optimized, it shows speedups at 2 to 4 threads and more than double the single-threaded performance at 16 threads already. This proves that OPAL's computation can be parallelized and that it holds potential for increased performance, especially with a solver that is refined further. Let us recap what we have seen. OPAL implements a novel, hybrid approach that is inspired by the Blackboard architecture. It combines individual, imperative analyses for flexible implementation with declarative specifications that guide a central infrastructure for modularization and parallelization. OPAL supports complex systems of dissimilar, interdependent analyses through the use of reified lattices that provide information to the central solver, through a two-phase structure for analyses that enables asynchronous computation, and through multiple options for both bootstrapping analyses as well as for the expression of analysis results. All of this at good performance, while being more general than the specialized DUPE framework, is 9% faster, and we also showed that OPAL's computation can be parallelized. So try it yourself. There's more information available at the project's website, and all code is available under a BSD license. There's also an artifact accompanying this paper that allows you to play with the different analyses available in OPAL already.